and this is the thing that's going to frustrate me to no end, and where I'm going to get irritated, and you're going to see the ugly side of me, is when people just give up and don't try. Like, I'm okay with wrong. I'm okay with struggle. I'm not okay with apathy. I'm not okay sitting there and giving up and saying, I don't know how to do this. Okay? Get out your resources, look through your notes, and pay attention to what's going on. Because we did multiple problems like this. Look at number 2 from the book yesterday on page 141. Jose, where's your book? Come on, get it out. And while you're getting your book out, I want to point this out. One student already said that this morning, this is way harder than what we just did, Mr. Kinney. No, what we just did, we spent 3.5 weeks on, so by the end it was easier. This unit is significantly easier than the last unit. This is something that we can master. We've only spent 1 day on it, so it takes time to learn. 141. Look at number 2 on page 141. No, yeah, number 2. What does it ask us to do? The new function g of x, x times f of x. That's an example when we dilate a function by something else. We have examples throughout. Notice how we then rewrote x times f of x as x times x plus 3. These are perfect examples of what to do within our book. And so when I look up here and I'm looking for f3 of x, where would I start? It's in the problem. I'm not trying to ask you to come up with something random. It starts with f1 of x. And what do we do in f1 of x?
Oh, it multiply by 8.
I didn't see that word multiply. Where'd you get multiplication from? That word dilate instantly tells us to multiply by x plus 3. And so, literally, based on what we saw in the book earlier, how would I rewrite this to represent the higher degree polynomial that we have?
Plug it in.
Plug what in? Negative 2/3, x plus 2. Now, what's a more mathematical term than plug it in?
Substitute.
Substitute it in. Alright, so is this correct? Sort of. What am I missing?
The negative before the plus.
Yes, we need the negative what before the parentheses? Can you pass it back here? So would this be correct? Negative 2/3. Remember, the negative 2/3 x plus 2, that is f1 of x. That all needs to go together. There's f3 of x. That's the function that I'm trying to sketch. And I will point this out, when just looking at this, because I do ask this question on the calculator, does anyone know what degree this polynomial would be? Why do you think that? Negative 2/3 times x would give me negative 2/3 x squared, quadratic. Also, I will point this out, how many zeros does this expression have? Just this one.
Oh, one.
That has 1. How many zeros does this expression have? Just 1. So how many zeros is that? 2 for degree 2. What key idea tells us that the degree matches the number of zeros or roots? What key idea? It's pretty fundamental to algebra. What key idea that is fundamental to algebra tells us that the degree and the number of zeros match? Fundamental theorem of algebra. So what fundamental idea to algebra tells us that the degree and the zeros match? The fundamental theorem of algebra. Not trying to trick you. Okay? Fundamental theorem of algebra tells us those things match. Now, here is the graph. I need someone to come up to the board and show us the starting point to sketch out this higher degree function, this F3. Come on, Naisha, where are we gonna
Oh, the
start?
start point. Nah, you got it.
Each said he was good.
I do the whole graph though.
No, I need just starting points. Come on, Tevin. Because I need us to talk through each piece, because we apparently were missing these pieces for some of us and some of our groups. You can do both. Okay, so what key points did Tevin just mark?
Zero.
The zeros.
Period, Tammy.
Remember, because I talked about this with one other group, I need you to pay attention, Mickey, because we're having a whole class conversation right now. What we're doing to get F3 of x is, what are we multiplying right here? What are we multiplying? Not the x.
The F1.
Notice f of x, which stands for y. I'm taking the y values from f1 of x, which means I'm also taking the y values from y equals x plus 3. I want you to think about this. Right. What is the y value at this 0? So if I multiply anything by 0, what do I get? 0.
0.
That's why the zeros match. If I take this y value, what's the y value for this expression?
0.
And what is, well, it'd be just the y value. Just the y value. Just the y value.
Negative 3. Negative 0. Negative 0.
X, remember, x-axis, so negative 3, the y is 0. So if I multiply by 0, what do I get? 0. Now, David, you did something that not everyone else did, but I think it's a good thing to do here. I think you led the charge on this. What did you do after you drew these points to try to help focus your attention on how to sketch? You did the dotted lines. Where did you put dashed lines? Through the zeros. Sorry, Naisha, I missed that. But remember, we're putting dashed lines through those zeros because, hey guys, what type of numbers are around 0? Like, what's above 0? Positives, and what's below 0? Negatives. And so those are our transition points. And so I like to put a dashed line here to make sense out of this. Boom. And so we now need to start looking at this. Now, this group up here, y'all were talking about negatives times positives, and that was good and important, but they were focusing on this idea, negative 2/3 times a positive 1x. What a does that give me for this parabola? What kind of a? This negative 2/3 x times this x here gives me a negative a, which tells us what about the parabola?
It's going to be concave down.
It's got to be concave down, right? Like, those are things we want to notice, but that's not what I want you to focus on, because we're going to go beyond just parabolas today. So how would I get what the left-hand side of this graph looks like? Someone come up and sketch it for us. Starting the sketch, just the left-hand side. Come on, I need you. I already had Tevin once, I need someone else. I appreciate you volunteering again, Tevin. Here we go. Like, you all have sketches on your paper. I don't know why anyone's scared to get it there. Okay? Anybody want to add on to or push back on what Lily Kate threw up there? Naisha, what do you want to do?
This was the top was like stop at 6.
Okay, so you're saying stop right here?
Yeah.
Okay? We'll talk about why in just a second. I do want to know that.
I know why.
It's not, but there's a good thing that Naisha and her group talked about to know that point right there. But remember, I did ask for the left-hand side, right? I wanted to the left of the dashed line. Do you know what it would look like to the left of that dashed line? Because that's a critical part that I need to see. Can I get someone to sketch what it looks like to the left of that dashed line, to the left of that 0? You all have answers. Come on, Ethan. Like, y'all making this harder than it has to be. Y'all all sketch something out. And we're too scared to get up here and try something. Alright, so let's talk through this. Ethan, why did you sketch all of this part of the parabola as being negative? Okay, but why, right, but why did you decide that these values should be negative right here? What's a positive times a negative? Which values? Of? Okay, so remember guys, these lines are my factors. These lines represent the factors. What type of values do we see up here for this line? Positives. What do we see for these values here? And a positive times a negative gives me, so to the left of that 0, all of these values are negative. Alright, Lily Kate, you started to graph this stuff in between my zeros. Can you sketch out the rest, like that entire section between the zeros? Right, so I was asking earlier for just to the left of that 0, and now I want what's in between those zeros. Just in between the zeros, in between those dashed lines. So, from here over to the next 0. Okay. Why don't you sketch it like that?
Because he said in between the dashed lines.
Right, but like, we talked about why these were negative. Why in the world did you make these
Because
values
those are positive.
positive? Why?
Because the x plus 2 is healthy.
One thing to remember, not just x plus 2, negative 2/3 x plus 2. So the blue line has what type of values? Positive. Is that the only line that matters though? No?
No.
What about the red line? It's also, remember how we're multiplying those y values. We're focusing on a positive y times a positive y gives me positive y's. Now, Naisha and Ethan, y'all, and I think, I don't remember if Trayon and Jose noticed this at first. I know Ethan mentioned this. Ethan, you noticed really quickly that this should be a y-intercept of 6. How did you know that? Remember, what are we multiplying, guys? The y values. What's 2 times 3? 6. You didn't have to get that, but that is a good thing to note. It's going to give me a little bit more accuracy with the graph. The y-intercept is an easy point to notice because when we dilate, we're multiplying the y values. I now need someone to come finish the sketch of this parabola. See, this is irritating. We've got 20-something students, and we're scared to stand up, or we just don't feel like standing up. Get involved in the learning process. Okay? It's okay. I will say this, if you haven't noticed with these parabolas yet, they tend to actually get pretty vertical near those zeros. But let's see what this looks like. Is our sketch pretty accurate? Yeah. Wait, you said you can't see it. I was say, do you know why you can't see it?
Because it's almost exact.
It's almost exact. Here is a black f3 of x all the way through here. Here's the only place really that it's off. Notice it stays pretty close. Right? Nice smooth curve, but that's okay. Listen, I only am really focused on, do you know the positives, do you know the negatives, things like that. I will point this out, and I will remind you, all of these y values are negative, but why were they increasing? To what?
To get to the zeros.
Remember, it's all about the zeros, right? We have negative values and we're trying to go towards 0, so boom. Then, Miracle, you with us? So then, it kept increasing, right? Because it had to go into the positives. Why in the world did it all of a sudden turn around and start decreasing? It had to get back to that 0, right? That's the focus, is it had to turn around to get back to the 0, and then it kept decreasing past that 0. Yes, 7. Say again. So if I were to multiply these, negative 2/3 x times x would give me negative 2/3 x squared. Notice this would be my a then. And so I knew it would be concave down just looking at that a. And like you would, please notice, I have not finished multiplying it. Mr. Kilpatrick is actually building a lesson to help us practice and understand how to multiply for Friday, but that's where we are right now, just looking at that leading coefficient. So, with that, we got to remember, guys, your education matters. Why are we here? One, we definitely need to learn social skills, and not just how to talk with friends, but when we say social skills, what do we mean? To learn how to make an argument, but even just social skills just means learning to talk with people for a productive purpose of learning from each other. Like, you will have colleagues that you work with for the rest of your life that you're gonna have to learn from them. Or you're gonna have to work with them to teach them things. You gotta develop those social skills to be able to work with somebody like that. So we're in small groups to learn how to do that. On top of the fact that when you are stuck, we need to stop building off each other's negativity or stop building off of the frustration and come in here and let this be a safe place to learn. Let this be a safe place to grow. That's why we're here, to be better than yesterday. And today is not better than yesterday, at least at the start. You come in with a bad attitude, it's going to be a frustrating place because I need you growing and learning. And you're all capable of amazing things. So, we are going to wrap up lesson 2, creating and graphing higher degree polynomials, practicing what we just did. And then we're going to focus on cubics after that with lesson 3. So we already talked about the fundamental theorem of algebra. This is going to show up throughout the unit. You need to know these concepts. You need to know those words and what they mean. So, an nth degree polynomial must have exactly n complex roots. They don't all have to be real, meaning that it could turn around above or below the x-axis without intersecting the x-axis, but it has that many complex roots. Alright, we have started this idea of dilating functions to create higher degree functions, but we are now actually focusing on sketching out those functions, looking at intervals of increase and decrease, and creating those higher degree functions. That's for second and third block, actually just second. We're here, I believe, on page 145, is that what you said?
I'm not looking for that.
Really quickly, I'm going to send out the files, or send the files back out from yesterday. Redistribute. Okay, Mickey, Desiree, it should be coming. If not, let me know, and I'll send it. Actually, it may not. So please note you need to be logged into these calculators, otherwise you won't get the file, which is why only 19 of 24 of us have gotten the file. And you need to move to 3.1 when you get the file opened. Oh, no, I just sent out the wrong file for some of y'all. Sorry.
Are we there for the
It was only to Desiree. Desiree, ignore the second file that I sent to you. The one that says 418, you should be opening the lesson 2 file. If you need to go into browse, then do that.
I got 418.
Okay, so if you got 418, ignore that, go to your documents, browse your documents, and look for the lesson 2 within this class's folder. Okay, so we should already have the first piece of this done from yesterday. This is again another example of what we just said. With number 1, we dilated the function f of x by a factor of x plus 3. So what did that mean? It says in a second, right? Dilating the function by a factor of x plus 3 gave us what? Just reading. Well, it gave us m of x, yes, but this language of dilating the function f of x by a factor of x plus 3, what does m of x equal? There we go. So we should also already have it written in our book. And I will point out, I like this notation better than this because we're starting with f of x and then dilating. Either way it'll work. And then, so what did m of x end up equaling? Okay. And then I will remind you, we already had x minus 1 graphed here, but it does say identify the zeros. How are we supposed to identify the zeros of that new function? How are we supposed to identify zeros of that new function? You could graph the second line. How else? Well, to use the zero product property, y has to equal, so remember, you can find your zeros without even graphing the line, and that's a good starting point. So, what were our zeros? X equals 1, and x equals -3. And also I would point out for this one, that's an x-intercept of -3, and what was the y-intercept? Come on, y equals mx plus b, what's the y-intercept here? The y-intercept would be a +3. Remember, we have a slope of 1, and I have rulers on the back counter if you want to use rulers to help you draw those lines. In fact, Ms. Bauer, can you go ahead and pass out a ruler to everyone? They're right next to the scissors. That'll help you draw these lines well. I'm just roughly sketching. Okay? And so, man, that is hideous. Okay, I gotta do better. Yeah, we did. But I'm reminding you of how we got there so that you can do it on your own in the future. And we are going to continue practicing these skills, which is why I'm getting you to get a ruler. Okay, so just like we just did, we have our zeros. Negative times a negative gives me a positive. So I know that I have positive values that are decreasing to that 0. What's a positive times a negative? Negative, so those positive values times these negative values give me negative. But what's it got to start doing eventually? It's got to start going back up. It's got to turn around and go back up to 0. And then to the right-hand side, we got positives times positives, which give us positives. Ooh, pulled Naisha there.
No way.
All right. So there's m of x. Then for number 2, it asks us to do what to m of x? Oh, yeah, that's all. Go back. What are we doing to m of x? Dilating it, so multiplying m of x by times x plus 2. And what function is that giving us? Oh, I didn't put a p there. Oh, I know why. What function does that give us? P of x. Okay. Now. So we've got p of x here. And so notice, we still have 2 of the same exact zeros. What's my last new 0?
-1. Oh, you said new 0?
Yep, the new 0. Remember, I already have these 2 zeros here.
-2.
You said x plus 2 equal to what? 0 for that 0. Okay.
And that's the y-intercept?
Remember, that's a 0. A 0 is the same as the what? X-intercept. So,
I'm asking a question.
look. So notice that's 0 is my x-intercept right here. What would the y-intercept for this line be?
2.
A positive 2. Remember, substitute 0 in for x to get a y-intercept. And so we do have 2 lines that are really close together there. Did we get a sketch of p of x yesterday?
Yeah.
Okay. Notice things change just a little bit when we get a third line in there. Now we have to multiply how many sets of values? 3.
It's cubic.
And that's what created a cubic. So looking to the left of the leftmost 0, I have how many negatives being multiplied? 3. And if I have a negative times a negative times a negative, I get a negative. And so all of these values are negative, increasing to this 0. When I look in between the next 2 zeros, which I don't like that they put the zeros so close, the red line has what type of values? Those are a little bit above the x-axis, those are positive. The black line has what type of values? Negative. And the line already graphed had, so I've got positive times negative, which gives me, say, Notice a positive times negative is negative, and what's a negative times negative? Positive. So notice it was negative, it increases into the positive, and very quickly has to turn back down to get to that 0. Oh no, my laptop's dying.
Yeah, he's got.
And regardless, you have a textbook. This class ain't ending anytime soon. Yep. That's over a month, it's 5 weeks. Unless you're a senior and then you have less time than that. You got a couple years still, you're just senior president. Alright. So from here, remember, okay, red line has what type of values? Positive. The black line has positive. The line already graphed had negative. What's a positive times positive? Times a negative. So remember, it hit the 0 and it started decreasing. But what do we have after it goes into these negatives? Another 0. So it's got to turn around and start to go back up. And then we look to the right and we have a positive times positive times positive, which is positive. Boom. Okay? It is just a matter of multiplying those factors. I will point this out though. We could have made our lives a little bit easier. This red parabola, wasn't that already the x minus 1 times the x plus 3? So if I had taken the red parabola and multiplied by my new line, it should have given me the same exact values. What's a positive times a negative? See how all those values are negative? Then here, looking at the red parabola, these values are negative, and the black line has negative, and what's a negative times a negative? Positive. And then to the, in between the next zeros, the parabola is still negative values, but the black line has positive values. What's a negative times a positive? So notice how the black cubic came down to the negatives, and then a positive times a positive is positive. So if you have the parabola sketch, you can more quickly get there instead of having to look at 3 sets of factors. All right, from here. So what do you notice, 3a, what do you notice about the dilations of each function and the zeros of each new function? Well, let's focus on this. Where are the new zeros for each new function coming from? Well, so like when we started out with f of x equals x minus 1, what was the 0? X equals 1. Then we developed m of x, which was f of x times, was it x plus 3? Okay, so what 0 do I have right away from before? From the one from f of x, which was x equals 1. Now, what's my new 0? From that new factor. So my question is, where are the zeros of each new function coming from? Where did this new 0 come from? But remember, m of x started with what? So what 0 did we already have automatically? F of x, right? So we kept the same 0. Like whatever 0 we already had, we kept. So where did this new 0 come from? Where did x equals negative 3 come from? Yeah, from the m of x. What part of it though? Y'all making this way harder than it has to be. The what? Say a letter. The x plus 3. The new 0 came from the new factor. Every new 0 comes from the new factor. That's it. That's all I want you to see, right? What we need to write here and make a note to ourselves is we keep the zeros from the previous function and get new zeros from where? From what? From the new factors. That's it. That's all you have to notice there. So, looking at B, how did the zeros appear to be related to the increasing, decreasing? Focus on in between the zeros. What happens in between the zeros for the increasing and decreasing? In between the zeros, what's happening to the increasing and decreasing? So right here, what's the function doing?
Decreasing.
And then it starts to
Increasing.
So in between the zeros, what's happening to the increasing and decreasing? Okay, so the increasing and decreasing is, right, in between my zeros, the increasing and decreasing what? Changes. Notice that's in between, not outside, but in between zeros. The increasing and decreasing changes. Why is that though? That's right. It's got to get back to the zero to get to the next zero. Notice after the last zero, does it ever stop increasing?
No.
No, why not? Well, there's not another zero to get back to, right? This is only increasing here because it's going to the zero, but it doesn't ever change because it's not trying to get back to a zero or change from one zero to the next. Okay, this is the last new thing before you get some practice with activity 2.3. What we have now is we are actually starting with m of x again, but we're creating the new function r of x. Where are we getting r of x from? From the new factor, right? So we're starting with r of x, which is, or where's r of x starting? That's what they have right here. And that, remember I said I don't like that notation because where are we really starting? We started, if you look at the language, with m of x, right? So we started with m of x, and what are we doing to m of x? Dilating by x plus 3. So you can write the dilation factor at the front, but it's more mathematically sensible to say times x plus 3, because we're dilating by x plus 3. Now I will say a lot of times when we do constants, we do put the dilation factor in front, but I think this makes more sense. And so we're trying to sketch this. Well, what do we already have graphed over there? We already have m of x. So what's the only other thing I still need to graph? Well, to get r of x, I have m of x. I need the x plus 3. So what key features of x plus 3 should we know so that we can quickly sketch it out? Okay, what's the 0 for that? Okay, so set your factor equal to 0 to find that 0. X equals -3. Are there any other features of that Notice that it's the same as one of the zeros that's already there. Are there any other features of that function that we should know right away, since it's y equals x plus 3? The y-intercept is 3. Anything else we should know? What's the slope? 1. Right? It's 1x plus 3, slope of 1. So I'm going up 1 to the right 1, up 1 to the right 1. Down 1 to the left 1, down 1 to the left 1. Use your ruler, sketch that line, graph that line as accurately as possible. Now, before we do the whole class discussion of this, I want you to work within your groups for a maximum of 2 minutes. I want you to sketch out what R of x is going to look like based on M of x and that new factor. So, sketch out what you think R of x is going to look like based on M of x and that new factor. Remember we had x-intercept is 0, -3 again, so we still have that. And we said the y-intercept was positive 3. And as long as you have the, be careful. Just notice that's 10 right there. So 2, 4, 6. Yeah. And so as long as you have 2 points, you can use a ruler to draw that line. Now I did some more points using my slope. Come on, let's sketch out what M of x is gonna, or R of x is gonna look like based on the factors, based on what we know about how those functions will look. What are we thinking? You don't know anything about what R of x is going to look like. Or what are the key points that we should always focus on? Jalen, this is on page 146. Let's start with zeros. Let's look around those zeros to figure out whether R of x will be positive or negative, things like that. What's up? I can see it.
It's about.
Okay. Wait, let's only talk through it. Remember, if I look at this, isn't that a y-intercept of 3? So 2. Also, it has a slope of 1, so up 1 to the right 1, or down 1 to the left 1.
How did you
It's a line.
like the actual grid? You see how it's
Cam, I need your head up. Thank you. Thank you, Jose. Thank you, Ethan. Thank you, Lila K. Thank you, Z. Thank you, Marshall. There we go. Starting to get some more hands up. So, let's look at this really quickly. Some of us are still making this harder than it has to be. Guys, what points do we need to start everything with? The zeros. That's it. Starting with my zeros. I already got that 0 marked. Here's my other 0. And then I look around the zeros. R of x. If I'm dilating, multiplying these two functions, notice I'm looking to the left of that 0. What do I know about R of x to the left of that 0? Negative. Notice M of x has what type of values? Positives. The x plus 3 has negatives. A positive times a negative is? Negative. So it's got to increase from those negatives up to that 0. Okay? Now, what about in between these two zeros? What would it look like? Say again.
It'll be positive.
Would it be positive?
And two negatives.
We got two negatives here.
Oh, no. It'll be
It's
negative.
gonna be negative again. We haven't seen that before. Does anyone want to take just a guess? I don't need it to be perfect. Just a sketch of what it might look like. Come on, Aisha. So, how's it going to go from being negative to staying negative? Just in between those zeros. Okay. So, what do y'all think? Is that going from being negative to staying negative? Yeah. Is it okay to just touch the x-axis and bounce away? Does anyone remember what we call that type of root? A double root. Remember, it's imaginary when we can't see it at all. But you see how it's touching and then bouncing away? Look at this function again. What was the expression for m of x? Times? Times. Now, the extra. Oh yeah. How many times does that -3 show up? And when you have a double root, what's it going to do? Touch and bounce away. Now, we'll point this out. There's something that Naisha did kind of mess up over here on the right-hand side. Does anyone know what it is? It's got to hit the 0, right? Remember, the whole thing is going away and then coming back up for that 0. And I will say, you probably just made it a little too deep there. I will say I would also go back and change this, knowing that I'm going to bounce away. I might start to, so like even I would have gone back and changed this. And I would have made it kind of curve earlier, bounce away, and then come back up to that 0. And then it should make sense that it's going to go through. And hey, what's a positive times a positive? Positive. There is my function. What type of function is this? Is it concave up? That's a great idea. Y'all agree? Concave up?
It's not a parabola, so it can't be.
Well, it's not a parabola, but it does have part that's concave up.
It's not gonna concave down.
But it's also concave down. Notice the beginning here. Look at this beginning right here. Is that concave up? No, that's concave. And then somewhere in here it transitions to being concave up. So when we get to these higher degree polynomials, we're going to have these terms in there that's going to have multiple concavities. Okay? So we'd have multiple places of concavity. So that's good to note. What type of function, by the way, is r of x? When you see that shape, what should you immediately think of? Is this one quadratic? The black function. Notice, remember, a quadratic has what shape, guys? A parabola. Is that black function a parabola? No. Is it what? Let me ask you this, how many zeros does it have? It has 3. Remember, David, one of those roots is a double root, so we're going to count it twice. Because I'm sure, David, what you were looking at has 2x intercepts, right? But even though it has 2x intercepts, it has 3 roots, which means it's degree 3, right? And so, hey guys, if I have x to the 3rd, what would I call that? Cubic. So what type of function is it? It's a cubic, right? It's just a cubic function. When I see this shape, I instantly think about a cubic function. That's it. Okay? So, I see a cubic function when I see this shape. I do want you to look again, so make sure you have your cubic drawn in there. Make notes to yourself, like, the reality of it is how are we getting these negative values here? Because some of us are still missing that detail. So for those of us who are picking that up, how are we getting those negatives? We didn't subtract anything. Keep thinking about it. Remember, guys, it's built off of these factors. What are we doing with those factors? We are multiplying. They're dilating. Right, positives and negatives. we're just looking at, right? So parabola. So like if you're missing this still parabola factors are what? Positive. The linear factors are negative. Sorry, parabola factor values. Linear factor values are negative, and a positive times a negative is a negative. That's it, guys. That's the whole thing. For those of us who are saying, hey, this is harder, no, we spent one day on it. This is much easier. All you got to do is sketch out that function and figure out what type of values are the factors, positives, negatives, and then multiply. You don't have to have perfect sketches, it just needs to be approximate. So, part B, I'm going to go ahead and just give this one to you. If we look at the function from question 2 and this function, do they have the same shape? So that's something that is what? And by the way, guys, you can go back to the previous page and look at it. So the shape, is it similar or is it different? Very similar, right? What's similar? Same shape. For what type of function is this? For the cubic? So remember that's degree 3 polynomial. But what was the difference? I think all three, or both of them had 3 factors, didn't they? So it had a double root. So how many x-intercepts did that have?
2.
It had 2 x-intercepts instead of 3, right? So this only had 2 x-intercepts for r of x because one of them was a what? What was one of those x-intercepts? Double root. And so we do want to notice at that double root, what did the cubic function do? What did that polynomial do? It bounced. It touched and then bounced away. But again, you can just multiply the factors to see what's going to happen. The positives times the negatives, right? So it bounced away from x-axis at the double root. Notice it did not go through there. All right. We need some practice sketching these, which is where activity 2.3 comes in. So, that should already be. Alrighty. So what I want you to do is I want you to get some practice in sketching these dilated functions. So notice in A here, you're starting with what function? F of x, thank you. And what are you doing to f of x? Dilating it by x, right? That's it. And so it gives us that x times f of x. And so as a reminder, before you do the rest of it and you do a couple more of these, when I look here, if I'm sketching that dilation by y equals x, what do I need to graph first? What do I need to graph in order to get this entire x times f of x? So the roots, the zeros, right? And we already have the zeros for f of x. And you'll see I have that 0 already as well. Where did that come from, though? promise you, I didn't pull it out of my butt. It's somewhere in that equation. From the 0 from the what? The x. The y equals x. Remember, the new zeros come from the new what? The new factors, right? The new factors give me my new zeros. And I would also point out that I can actually sketch this line because what do I know about the line? Yeah, it's got a 0 of x equals 0. What else do I know about it? It's a line, guys. It's got a slope of 1. Also, this one's literally y equals x, so whatever x is, that's what y is. So when x is 2, what is y? 2. When x is 4, y is?
4.
When x is negative 2, y is? Negative 2. So there's a couple of key points to help me graph my line. So let's work through the next 10 minutes, get as many of these graphed as possible to give you some practice with sketching these things.
Mr. Kennedy, come here.
Mm-hmm. Let's actively collaborate. Who said Mr. Kinney come here?
Try on.
Come on, let's get working. Let's graph. A through D. As much as possible. You have 10 minutes, that's it. Well, if y is equal to x, whatever x is, that's what y is. So when x is 0, y is 0. When x is 2, y is... Now that's just that one specific case. What I would also remind you, specifically for like these, if I'm dealing with y equals x minus 2, that's mx plus b. There's my y-intercept, and my slope is 1. So I can use that to graph this line. And I would use that ruler to graph that line. So I'm using my slope and my y-intercept. You can, yeah. Okay. And also notice the slope here is 1 as well. So I would use that. So guys, check in with each other. If you're stuck, talk with each other. And by the way, we're not done here, remember? Because all I did was give you the y equals x. We need x times f of x. So draw your line in there. Right? And we still need to draw the dilated function. Yeah, do the thing. Okay, now that's the roots of f of x. What are we dilating f of x by?
The line. So, look, it is extra.
That's f of x. We're sketching x times f of x, which is why I literally just took the time to draw those points up there for y equals x. Remember, I literally just went through if y is equal to x, if y equals x, if x is 2, what is y? 2. If x is 4, y is 4. This also, remember, is the same as slope intercept. 1x plus 0, y-intercept is 0, the slope is 1. That graph, so you sketch it out.
Or you're right.
So, maybe eventually, but remember, we're graphing y equals x, right? What type of function is y equals x? Right, so draw a line, and then we're going to, because that's just the y equals x piece. Then we get x times f of x.
This is f of x, and then this is the extra factor, and right here we have f of x. So to sketch this, what do you need to point out?
Look, right here.
What character?
You see how this is a 0?
To these of x.
Okay, so I'm going to look to the left of the 0.
In order to
Because what I'm literally doing
find the
is I
shape.
am multiplying f of x, which is this parabola, by y equals x. I'm diagonal, so I'm multiplying these values.
Do you know
If I look at this part of the parabola, are those y values positive or negative?
occur like
Okay, these are, and so if I take a positive times a negative, I get, so leading up to this 0, I have negative values, but they're increasing to get to 0. It doesn't have to be a perfect sketch, but I know I have positives times negatives to get up to that 0.
So
Then I look to the next zero, and I look in between my zeros now. When I look at this parabola, in between those zeros, the parabola has negative values, the line has
This
negative values, and what's a negative times a negative?
How down.
Positive, right? So it goes up into the positives and comes back down to the next zero. Okay, keep it going.
Right, so looking at this one, where are we?
Let's make sure we keep working with each other, check with each other's answers, because Naisha, you and, Ethan have different answers. How'd you get a line?
I don't know.
Huh?
Do you mark them on there?
You know, f of x is already here, right? So you didn't need to draw the x minus 1 and the x plus 1. You can, because f of x is x minus 1. Isn't that a parabola? X minus 1 times x plus 1 is this parabola right here. That was already graphed. You just need to graph x, this part right there.
So now we can focus on.
Now,
Do you,
so like you just add an extra step. Now notice, what's a negative times a negative times a negative? So like the dilated function is a negative, but you made your life actually harder than it had to be because you already had the parabola. What's a positive times a negative? See how that's already, that's the same thing. You didn't have to draw all the lines because you already had this parabola. No, I was just doing this because we're trying to sketch this dilated function. You made it like part of the game. The graph is already there. Push it back. See how those zeros are these zeros? Right? You just had to graph the x minus 2. Well, it depends. What are you referring to? The 0 or the y-intercept? In this case, so if I'm trying to graph y equals x minus 2, my y-intercept, now if I want my wouldn't I have to end up adding 2? So it would be a positive 2 for the x-intercept. It would now use your ruler to draw a line between those 2 points. And now you'll have the linear factor of f.
yeah.
You didn't actually do 8, so maybe you go back and do 8.
Figure out how to.
Why did you finish this one? Where did we get stuck?
Right.
Hold on. Focus on the graph. The whole point of graphing is you can see the values. Positive times a negative gives me a, so I've got negative values leading up to 0. Then, in between these zeros, negative times a negative is a,
You must want me.
then in between these zeros, negative times a positive is a negative. And to the right of the 0, I have positive times a positive, which is, that's all you're doing. Notice, like, don't look here. You have that graphed already. So boom, graph this, and then multiply your positives and your negatives. Same thing here. Start with, say again. What? No, I know you're not doing one of that. Work with Jacoby to make sense out of this. Yo, what's going on over here? I keep telling you to bring your baby. Then put a note that says alarm right now and get your book and get out.
No, he's not.
Yeah.
I'll never see them.
I've done a couple of this. They literally have f of x already graphed right here, right? You now have y equals x.
What is that?
Look around your zeros.
But the answer.
What are positives times negatives?
If I.
Positive times negatives. So, I'm going to take this dilated function, I'm going to take it as, and it's coming up to
That
this.
did not. So I had to put 3.
Look at this.
Negative, I mean, hey, one of them. Right, these guys are positive, but it's got to get back to the next
So
zero.
it puts
Turn
it
it
around
around.
X value. And that X value,
I'm telling you, negative, positive, negative.
Go ahead, figure it out.
Positives are,
Does that make more sense? Because that's what we did here, it's just, there's nothing else we
so you
can do.
use the sketches and you have to figure out where it'll be positive and where it'll be negative.
So.
Okay. Ladies and gentlemen, where are the new zeros coming from? The new factors. That's something I need you to recognize. We're about to go over a couple of these. But the new zeros are coming from the new factors, and that's it. Notice f of x is already graphed here. You didn't have to rehash the x minus 1 times the x plus 1. You were given f of x already graphed. The only new thing you needed was the new factor y equals x, which was this line right here. So y equals x, f of x, and I am dilating f of x by x. And I focus around the what? What key points tell me where the dilated function will change from positives to negatives? What number's in between positives and negatives? The 0, right? So the zeros tell me where it changes. That's not right. So I draw a dashed line here just to help me focus my attention. Notice, what's a positive times a negative? And so all of the dilated values will be negative coming up to the 0. That's it. Now I look in between the next zeros. When I multiply the parabola values by the linear values, what do I get? What kind of numbers? Guys, I can't keep telling you whether it's positive or negative for each of the factors every single time. The dilated function is going to have what type of values? The dilated function has negatives? So it's going to bounce away and go back into the negatives here? No? Why not?